Hi guys, I think I'll be starting right now. I hope you had a safe and healthy weekend. Today we're going to talk about atomic theory and we'll have a review of measurements. So what we're going to cover today, we're going to start covering what is an atom and see Dalton's atomic theory. Then we're going to learn what the atomic number is, what atomic mass is, and what is the nuclide symbol. And then in the very end, we're going to review significant figures. Thank you to everyone who did the homework. You guys have done pretty well on the homework. And thank you for completing it. So let's start out with Dalton's atomic theory. So he has 4 postulates in his atomic theory. His first postulate is all matter is comprised of small indivisible particles called atoms. In chemistry, the smallest particle is called an atom. An atom has 3 major parts. As you can see, there's the red particles with a positive charge. Those are called protons. There's these gray spheres with no charge. They're called neutrons. And then there's those blue spheres with negative charge, and those are electrons. So the 3 parts of an atom are protons, neutrons, and electrons. So the protons and the neutrons lie in the center, and the electrons rotate around the center. This picture is kind of misleading because it shows that the nucleus isn't that much smaller than the space electrons orbit in, but that's completely wrong. So a good analogy of the spatial distribution of an electron is in a football stadium. If you have one marble that is the size of a nucleus, the electrons rotate around the whole stadium. So as you can see, it's probably the nucleus is very, very, very small, and the electrons orbit a large amount of space. And that's the atom. So his second postulate is an element is a type of matter that contains only one type of atom. So here's a periodic table. There's 118 known elements so far. Each element contains only one type of atoms. So for example, this 1H, that's hydrogen. The element hydrogen only contains hydrogen atoms. And this one is He, helium, and helium, the element helium only contains helium atoms. So what determines if something's called a helium atom or a hydrogen atom? Well, basically protons are the only thing that determines an atom. So everything with 1 proton is always a hydrogen atom. Any atom with 2 protons is a helium atom. So basically the protons determine which element it is. An element only contains one type of atom. So hydrogen only contains 1 proton, and each helium atom only contains 2 protons, and so on. The third thing in Dalton's atomic theory is a compound is a matter that has atoms that chemically react in a fixed proportion. So for example, we all are familiar with water as a compound. It's like essential for life. It always has 2 hydrogen atoms reacting with 1 oxygen. So in any sample of water, no matter if you have 5 milliliters or you have a gallon of water, the ratio of hydrogen atoms to oxygen atoms is always 2 to 1. So his third theory says a compound has fixed proportion of hydrogen and oxygen atoms. So his last theory is a chemical reaction rearranges the atoms but does not destroy the atoms. So I'll give an example. This is what a chemical reaction looks like. So this to the left of the arrow, those are called reactants. And to the right, these are called the products of the reaction. And this is the reaction arrow, which means a chemical reaction is taking place. So Dalton's last theory says, however many carbon atoms you have on the left, you have the same number of carbon atoms on the right. So this shows that we have one carbon atom on the left, one on the left, and then we have one carbon atom on the right. So the carbon atom doesn't get destroyed or changes to a different atom. There's always one carbon atom on the left and one carbon atom on the right. The same is true for hydrogen. So a subscript means there's 4 hydrogens in one molecule of CH4. So there's 4 hydrogens on the left, right here. And then on the right, we have a coefficient. So that means we have 2 water molecules, but each water molecule has 2 hydrogens. So actually we have to multiply 2 by 2, and we actually get 4 hydrogens on the right as well. So there's an equal number of hydrogens on the left and the right. And finally, we can show the same for the oxygen. So here's a leading coefficient of 2, which means we have 2 O2 molecules, but each O2 molecule has 2 O atoms, shown by this subscript. So there's actually 4 oxygen atoms on the left. And then on the right, we have 1 molecule of CO2, so there's 2 oxygen here. And then we have 2 molecules of H2O. So there's 1 oxygen in each molecule of H2O, and we have 2 molecules of H2O, so we have 2 oxygens here. So we have 2 plus 2 equals 4. So we've basically seen that we have the same number of each atom on the left and the right of the arrow. So Dalton's atomic, the last theory says the atoms are not destroyed. Does anyone have any questions? If you have any questions, just leave it in the chat. Okay, I guess I'll move on. Okay, so that was the 4 principles of Dalton's theory. Oh, can you show us the previous slide? Second to last. Okay. Is it this slide, Sophie? Or was it the last slide? I'll assume it's this slide. Sorry, guys. Someone's asking a question in the chat. Okay, we can move on now. So now we're going to talk about atomic number, atomic mass, and nuclide symbol. So atoms, like I said earlier, an atom contains 2 parts, the nucleus and the electrons. So the nucleus contains positively charged protons and neutral neutrons in the core of the element. As you can see, the protons are blue and the neutrons are red. So they're in the core of the atom. And electrons are negatively charged particles that exist outside. It's attracted to the neutrons because electrons have negative charge and they're attracted to the positively charged protons. That's why they sometimes orbit like the atom, but it's not in like a orbit of planets in a sun. It's not circular or elliptical. It's a random orbit around the atom. So now we're going to talk about atomic symbol. So each element has an atomic symbol, which is just a 1 or 2 letter notation that to represent an atom. So it's basically a shorthand for writing an atom. Instead of writing the whole name of the atom out, we're just having a shorthand. An example is H is the atomic symbol for hydrogen. He is the atomic symbol for helium. This is actually weird, but Au is the atomic symbol for gold. It's because the atomic symbols, they're not all from English. They might be from some other country and using abbreviation from another country. So that's why we have some weird atomic symbols that you'll never think represents the atom. And then Ag is the atomic symbol for silver. So every element on the periodic table has an atomic symbol letter notation, which you can easily look up if you want to know. Someone asked me to go back to the previous slide, so you guys don't have to take notes on everything, like just the most important parts. And I'm gonna post this PowerPoint after class with notes as well, so you can take notes later. Like the most important thing in a lecture is you understand what I'm talking about. Oh, someone told me that Aurum is Roman for gold, and that's why gold is Au, and argentium is Roman for silver. So that's why they have the weird names. Okay, so now we talked about atomic symbol. Now we're going to talk about atomic number. So we define it as Z, which we're going to use later on in helping us with the nuclide symbol. So I want you to know the letter as well. The atomic number Z, it's basically the number of protons in the nucleus of an atom. So an element is a substance whose atoms all have the same number of protons or the same number Z. So in this element, the positive red spheres are protons. So can you PM me the answer? So what's the atomic number Z for this element right here? The atomic number Z is the number of protons. So we're basically counting the number of protons in the element. So there's one proton right here, and there's one proton here. So we would write Z equals 2. I hope that makes sense. Atomic number is basically just the number of protons. And a lot of you have gotten it right. It is 2. And each element always has the same number of protons, so a Z element. An element's basically a group of atoms. I explained that on my first slide. Actually, an element is basically consists of a group of one type of atoms. So basically atoms here. You can just say atoms instead of elements. They're roughly the same thing. Okay, so now let's go through a few more examples. So let's start with the most abundant element in the sun, which is hydrogen. It has an atomic number of 1, so Z equals 1, because it only has one proton. So as you can see in a hydrogen atom, there's just one proton. So then we can say Z equals 1. Now, if you look at a periodic table, the atomic number is usually on the right, or sometimes it's right here. It basically tells you how many protons are in a given element. So for each hydrogen atom, there's always one proton. And it would always tell you. And then here's the atomic symbol, which we talked about earlier. H is for hydrogen. And then sometimes they would give you the name down here. Sometimes they'll give you a number like 1.008. We're going to talk about this in the next few slides. I think it's the atomic mass, so how much each element weighs, basically. Okay. And now let's do it again for helium, which is the exact same one you guys all got right earlier. There's one proton here. There's one proton here. Remember, the protons are the positively charged particles. The neutrons or the neutral ones are the green ones right here, and the electrons are yellow. So to determine an atom, we only look at the number of protons, so the red ones. We don't care about neutrons or electrons. So I had a question that asks, how do they weigh the elements? In the easiest sense, basically each proton is 1 unit, 1.0 unit, and each neutron is 1 unit as well. And electrons are basically, the mass is negligible, so they basically count for 0. So basically how they weigh the unit is you add up the number of protons, which stand for P, and neutrons. So as you can see here, there's 2 protons, 2 neutrons, and we get around 4. This number is really close to 4, so that's how you calculate the atomic mass. I had another question that says, will the electrons and neutrons always be the same? No, the electrons and neutrons do not have to be the same. They just are for these specific elements. But there can be different number of protons, neutrons, and electrons in any atom. We'll get to that later. But what determines an atom is the number of protons, and that's why we use a letter Z to represent 2, because in every single helium atom, there's always 2 protons. We cannot say that that's true for the electrons or the neutrons, but it's true for all the protons. And see, here's the atomic number again, Z equals 2. Here's the element symbol, and here's the mass. So we're going to have some example problems. Please PM me the answers once you get them. So what is the atomic number Z for beryllium? Yep, I'm seeing a lot of correct answers in the chat. So remember, atomic number is basically number of protons. And protons are positively charged molecules. I mean, subatomic particles in the atom. So the protons are the red ones. So there's 1, 2, 3, 4. So you should get Z equals 4. A lot of people got the correct answer. So that's great. We don't consider electrons, which are the blue ones, or we don't consider the neutrons. We'll consider the neutrons later, but right now for atomic number, we only consider protons. So the correct answer should be 4. And I'll give you another problem just so you can practice it again. So what is the atomic number Z for carbon? So here's a carbon atom. You can't see the electrons yet, but do your best and try to count the number of protons. Okay, good. A lot of people have the right answer. So we basically count the number of positively charged. So there's 1 here, 2 here, 3 here, 4, 5, 6. So there's 6 positively charged protons. And remember, atomic number Z is the number of protons, so Z equals 6. We do not consider, again, we do not consider number of neutrons or number of electrons when we calculate the atomic number, but we will consider them later for other things in the atom. Okay, so now let's talk about elements. Like I said before, elements must have the same number of protons in each atom. So basically, an element has the same number of protons. So if you have 1 proton in the atom, then it's a hydrogen element. If you have 2, it's a helium. It's predetermined, and you can look up the periodic table. I had a question, what's beryllium? So beryllium is the 4th element on the periodic table. It's basically, it just has 4 protons. So that's the thing about beryllium. It basically has 4 protons, and you can see the properties that it exhibits by looking at periodic trends, which we will not cover today. So like carbon was the other example I had earlier. So carbon, basically, it's an element. Beryllium and carbon are elements. So they're a type of atom. So this atom is called carbon. And it's determined by the number of protons in it. Okay, so elements may have different number of electrons, and those are called ions. They can have different number of electrons because atoms can easily lose or gain an electron. So there can be different number of electrons in the atoms, and they might have different number of neutrons as well, called isotopes. A common example of it is, I'll go back to carbon. If you see in this picture, there's 6 neutrons and 6 protons. So we call that element, this specific atom, carbon 12, which is the most common type of carbon atom. But there's this carbon atom, which is called carbon 14, which has 6 protons and 8 neutrons. It's a rare type of carbon, but that's how geologists use carbon dating to find the age of a compound. So you can have different type of neutrons, number of neutrons, and that might help in a variety of different things like carbon dating, like carbon 14, for example. And if you have a different number of neutrons, they're called isotopes. So now we're going to cover the next thing, which is atomic mass. Like I said earlier, a proton basically has a mass of 1, a neutron has a mass of 1, and an electron has a mass of 0. A proton and neutron are like 1,800 times greater than the mass of an electron. So the mass number, which we'll define as A, is the total number of protons and neutrons in an atom. We're not considering electrons. And yes, I would send the slides to everyone. I'll post them on Google Classroom after this lesson today. So helium, let's find the atomic mass of helium. So there's 2 protons, so protons. Remember, protons are positively charged. There's 2 of them. And then we count the number of neutrons. I'll change my color to green so it matches this. There's 2 here. So remember, the atomic mass, A, is the total number of protons and neutrons. So we just add up these numbers and we get 4. So A equals 4. So that's the mass number. And this number is the number you saw earlier on the slides that's on the bottom of the periodic table. It was like 4.003, which is pretty much 4 on the, sorry for this scribble, in the periodic table. And that's the mass, which is the atomic number A. So it's basically the sum of protons and electrons. So please PM me the answer when you get it. So what's the mass number for A for beryllium? Remember, this is a beryllium atom right here. And we want to calculate the mass number. Okay. It's good. A lot of people got the right answer. So remember, mass number A is protons plus neutrons. So we basically count everything in the center of the atom, which is here. So we can see the number of protons, which is 4, and then the number of neutrons, which is 4. And 4 plus 4 is 8. So we write A equals 8. So that's how we do an example of it. And the answer is 8. I had a question that was asking if you're covering positrons. No, positrons are a type of atom that an atom emits if it undergoes nuclear decay, which is beyond the study of intro chemistry. You'll probably start learning positrons in AP Chem, maybe. It's not covered on the test, but some teachers cover it. Positrons basically exit the nucleus, so they're not a part of the atom anymore. Protons are the positively charged subatomic particles in the nucleus. In this case, they're the red particles right here, where my mouse is holding. Okay. Here's another example. This one might be trickier. We want to find the mass number A for carbon. It might be a little harder this time counting the protons and neutrons, but try to do your best and PM me when you got the answer. I'll give you a few more seconds to answer it. A lot of you got the correct answer, which is very good. So basically, remember, A is number of protons, which is the positively charged part, and neutrons. So the positively charged particles, there's 1, 2, 3, 4, 5, 6. And then the neutrons, there's 1, 2, 3, 4, 5, 6 as well. Just a reminder, we don't consider these electrons when we're doing mass number because they have basically a mass of 0. And each proton and neutron have a mass of 1, which we arbitrarily defined. So we get A equals 6 plus 6, which is 12. So the correct answer is A equals 12. I hope this was pretty easy for you. So now we're going to be putting together everything. So we're going to combine atomic mass with the atomic number, the atomic mass, which is A, and the atomic number, which is Z, when we have a nuclide representation of an atom. So a nuclide is basically an atom with atomic number, mass number, and atomic symbol. So it puts everything we've learned together. So as you can see, any nuclide is in the form atomic symbol, which is AS, and then their mass number, which is A, which we define A, and then we define the atomic number, Z. So it always is in this form. So as you can see in this example for sodium, which is Na, so this is the atomic symbol for sodium. So we know it's a sodium atom that we're talking about, or element. The atomic number is Z. So remember, Z is the number of protons. So we know it has 11 protons. And then the mass number is A. So remember, A equals protons, which I'll abbreviate with P, plus the neutrons. So the atomic number gives us the number of protons. We know A is 23. So we can basically find the number of neutrons given A and Z. We can do simple subtraction and get N equals 12. So this atom basically tells us it's a sodium atom. It has 11 protons. It has 12 neutrons. And we could even determine the number of electrons. Since there's no charge on the sodium, if there was a charge, there'll be like a plus or like a minus on top. We know that each atom is neutral because neutral atoms are the most stable atoms. So we know the number of protons equals the number of electrons. So in fact, we know every single number of the subatomic particles by using A and Z. So remember, A is the sum of neutrons and protons, so things that have mass. Z is the number of protons, and in a neutral atom, which everything we're going to cover today is neutral, we know the number of protons equals the number of electrons. So given a nuclide, we can determine exactly the element. So that's the benefit of a nuclide. So that's why this is pretty important. And as I was saying, in a neutral atom, there's an equal number of electrons and protons. So, and everything we're going to cover today would have an equal number. So here's an example problem. So please type in the nuclide symbol in the chat when you have it for beryllium, and the atomic symbol is Be. So I know it's hard to do uppercase and lowercase. So you can type your answer as A/Z/Be, if that would be easier. So you can type it in that format. Oh, some of you guys are good at tech and you could figure out a cool way to make it work. So the atomic number is the number of protons. So you basically count the number of protons. So Z is number of protons. I hope. Yep, a lot of you, everyone who has answered got it right so far, which is good. So let's work through the problem together. So the easiest thing first is to calculate Z, because it's just calculating how many protons. So we can just count the protons, which is 1, 2, 3, 4. So Z is 4. So we know it's 4 on the bottom. The atomic symbol is Be, which I gave you. If you didn't know that the atomic symbol for beryllium is Be, you can just look it up online or look at a periodic table. It'll tell you the atomic symbol. And you get used to them after practicing them a lot. And the last thing we do is A. Remember, A is the atomic mass. So it's the protons plus neutrons. There's 4 protons, there's 4 neutrons, which are the purple spheres, and we get a total of 8. So we get 8 for BE. Remember, we do not consider the number of new electrons. But like I said in the earlier slide, the number of electrons in a neutral element or atom is the same as the number of protons. So as you can see, there's 4 electrons here. The shorthand notation for electrons is an E with a minus. That's the same thing as electron. So as you can see, there's an equal number. But when we do a nuclide symbol, we don't care about the number of electrons. It has no effect into our nuclide symbol. Okay. Now try this one. What's the nuclide symbol for this carbon atom? The atomic symbol for carbon is C. Please answer. Please submit your answer in any form you can in the chat. And be careful on this one. It's kind of hard counting the neutrons sometimes. And if you guys don't mind, I would prefer you to send them with Z. Wait, never mind. Sorry, guys. I confused myself. Oh, yeah. Submit them in A, Z, and then C, which is for the carbon. Some people have the order reversed, which is kind of bad. What do they mean again? A is the atomic mass. Z is a number of protons. And C is the element. Okay, a lot of people have gotten it correct. So I'll go through the solution relatively quickly. So let's start with Z, the symbol. So the symbol is carbon. It's a carbon atom. So we put C. And then now I like to do Z first, which is basically counting the number of protons, which is 6. And then the number of neutrons. I mean, there's 6 protons. There's 6 neutrons. It's kind of tricky to see this one, I do have to say. And then we add them up. So we get A is 12. So it's a 12-6 carbon. So that's the correct answer. So if you were sending it to me, I would like 12/6/C, or if you could even format this cleverly, it's pretty good. Everyone ended up giving me the right answer, so that was good. You guys understood. Okay. Yeah, some people basically sent 3 lines and they indented it. So I thought that was pretty cool that they could manage to do it through the chat. Okay, now let's do it for this one. We're not given the picture anymore because if you have 38 protons and 50 neutrons, that'd be way too much. But please, in the similar form, do either do A, Z, and then the S, R, or some, if you can figure out how to do it in a clever way, do it. But do the same thing, but this time we don't have a picture because I couldn't find one that had so many protons. Okay, a lot of you have done it correctly, which is really good. I like how all of you took the suggestion of 3 lines. I'll give you a few more seconds. Okay, so I'll work it through with you guys. So basically, remember Z is the number of protons. So Z equals 38 because we're given that. And then A is the number of protons plus neutrons. So that is 88. So we do the element SR. We'd go from A to Z. I like the naming because it's the letters, because it basically tells us the order to put them in so you don't confuse yourself. So A is first in the alphabet. So I remember A goes on the top. So 88. And the bottom is 38. And everyone who answered got it right. So that's good. So here's our next example problem. Try this one. A chlorine atom has 17 protons and 18 neutrons. So what's the symbol? Remember, you can do it in form AZCl or any way you wish, if you can figure out. Okay, everyone's got it right so far. So remember, Z is 17 because that's the number of protons, which are positively charged. A is the sum of protons and neutrons, which is 35, and the element is Cl. So we'll get 35, 17, Cl. So we all got that right, which is good. So that wraps up the atomic theory for today. We're gonna pick up more atomic theory in the next class. But right now, I wanted to wrap up the importance of significant figures. I didn't do a good job explaining them last time. So this time, I hope my rules are more precise and people would understand them better. So significant figures, they're important to estimate uncertainties in values calculated from the lab because equipment are not always precise. There's always some experimental error. And significant figures basically show us how precise our measurements are. So if you can see in this drawing to the left, suppose like shooting a dart is basically the accuracy. So in the first case, look at the dots, they're like spread out. So we're not really sure if it measures the right value because the numbers are all spread out. So we say that has low precision. So it's not precise. So if we had to, if this was like a measurement, like if you're measuring something on a mass, like pretend this is a scale and this is like an object on the scale, and it's that the values are like so spread out, then we could probably only measure it to like 1 decimal place, 2.3 grams, because it's not precise enough. We can't tell because there's experimental error. However, if the measurements are like extremely close, like here, then we could have more digits, like 2.30 grams. We have an extra digit because we know it's more precise because the values are closer together. So we have more precise. In this example, we don't want to add extra zeros at the end because an extra zero adds an extra significant digit, and that has precision issues because it's not precise, but putting extra zeros makes it seem more precise. So you do this in like with rulers, balance, thermometers even, and anything in the lab that measures a value. So we want to know the precision in the value, and that's why we need to learn significant figures. And then going back to my example earlier, suppose we have something on here that is 2.30 grams. We need rules for adding, subtracting, multiplying, and dividing significant figures because we want our answer at the very end to reflect how certain we are of the answer. So if we have a better scale, we might have like 2.300 grams, and that signifies that we're more certain that it's closer to this value. But this scale is probably pretty old, so we can only have like 2.3 grams, 30 grams, which has 3 sig figs, compared to this one, which has 4. But the 4 shows that we're more precise in our answers. And then if we're multiplying it, for instance, if we're multiplying it by a constant, we want to reflect the number of sig figs at the very end, because we want our answer at the very end to show how many how sure we are of our answers based on the beginning. In mathematics, you don't have to deal with this issue. We multiply every number precisely and usually round to like 3 decimal places. That's a good rule. But in chemistry, significant figures are important. You have to have the right number or your teacher will dock off on you. We don't want too many significant figures and we don't want too little. So we have to keep that in mind. Someone raised their hand. Do you have a question? You can unmute your microphone if you can. A crazy video game. Okay, there's 2 people who raised their hands. Crazy video games. Do you have a question? No? Oh, he said, why do we not want to use the max significant figures? I'm using chat. So basically, it's not a max or a min. It's basically the type of device and how precise a device can measure. Like, this is probably a pretty cheap balance, and it's not precise. But at some high scale research balance, it's more precise and you can have more decimal digits because it's more certain of the values it measures. So significant figures basically tells us how precise our measurements are. We don't want to add or subtract more uncertainty because that would lead to erroneous beliefs, having stuff more precise than it is. Okay, so now we're going to review the rules. There's 4 rules. After these 4 rules, I have 5 example problems to test your knowledge at the very end. So our first rule is all non-zero numbers are significant. So 11. So what's non-zero? So that's any digit from 1 to 9. So if you have any digit with 1 to 9, it's an easy, they're all significant. So like 11, both of those ones are significant. So we have 2. 298.1, all 4 of those digits are significant. So we have 4. This big number, 22,198.234, they're all significant. So we have 8. So basically, if it's a non-zero digit, it's easy, they're all significant. The hard parts are about zeros. So our first one is leading zeros, which are zeros that precede non-zero digits, are not significant. So I want to clarify what leading zeros are. So you look at the first non-zero digit. So in this case, 0, 1. So leading zeros are zeros that precede non-zero. So they're to the left of non-zero. So that's this 0 right here. So the rule states that leading zeros are not significant. So that's not a significant number. So another example is 0, 2. That's a leading 0. They're not significant. So only 2 is significant. 1 sig fig. And 0, 0, 2 Also has one sig fig. Yes. Someone told me that zeros that don't impact precision are not significant. That's completely true. So these zeros in the beginning do not impact precision, and they're not true. And then it's hard for this one because these 3 zeros are also leading zeros because they're to the left of the first non-zero digit. So it only has one sig fig. And all of these zeros are not significant either. It only has 2 sig figs. So now let's go to rule number 3. I define something called captive zeros, or zeros between 2 non-zero digits, and they are significant. So this 0 is captive between the other 2 zeros, so all of them are significant. In 2002, those 2 zeros are captive as well, so they are significant. So everything's significant for 4. In this case, this 0 is captive from 2 to 0, and all of these zeros are captive from this 2 to this 2, so everything is significant as well. In this case, we're bringing back the last rule as well. These zeros are leading zeros, they're not significant. But these zeros are captive because they're between 2 non-zero digits. So all of them are significant. So we have 4. And our last rules, this is the one that can get slightly confusing. Trailing zeros, which are zeros to the right, are significant only if there's a decimal point. So I brought this example because although there's a decimal point here, these are not trailing. They're not to the right of a non-zero digit. They're to the left. So they're leading zeros, and leading zeros are never significant. So there's only one sig fig here. In this case, it's 100. You might think it's 3 because this is a trailing 0, but the condition states that they're significant only if there's a decimal point. There's no decimal point here, so these are not significant. So there's only 1. But however, if we add a decimal point here, then these become significant. So all 3 of them are significant. In this case, there's a decimal point. So all 5 of these are significant for a total of 6. 2020, 2s are significant. This is a captive 0, which is between 2 sig figs. That's significant. And the last one, this is a trailing 0, and it's significant only if there's a decimal point. There's no decimal point, so that's not significant. So there's 3. But however, if we add a decimal point, all 4 of these become significant. So we have 4. A decimal point basically says we have a more precise equipment and we can measure it more precisely. I had a question that says, what if I want to mark 100 as 2 sig figs? You really can't do that writing numbers like these, like this, but you can do scientific notation. You could write your number like this, 1.0 times 10 squared. As you can see, there's a 0, so trailing zeros are significant, so there's 2 sig figs here. So if you want to change the number of sig figs, you basically have to use scientific notation, which is kind of a pain, but that's what you have to do. I had a question that says, wait, but shouldn't zeros at the units digit count for 20.0 should be 5? Yes, if you have a number 2020.0, there are 5 digits. You're absolutely correct. But in this case, there's not that extra 0 at the end, so there's only 4 sig figs here. So let's go through the 5 practice problems really quickly. Okay, please put your answers in the chat. How many sig figs are in 1001? We're almost out of time, so. Okay, everyone who has answered got it correct. Remember, the 1s are significant, These are significant, and all of these zeros are captive, so they're also significant. Remember, captive zeros are between two non-zero digits, so we have 4. How about this one, 90.0? Okay, a lot of people have got this one right too. This 9 is definitely significant. These two are called trailing zeros. So we have to look at it. If there's a decimal point, there is a decimal point. So all of these zeros are trailing and are significant. So there's 3. Note if I had 90 instead with no decimal point, then only 9 would be significant. Because for trailing zeros to be significant, there must be a decimal point. How about 2000 with a decimal point? Crazy video games, do you have a question? Can you type it through chat? Oh, never mind. So remember that there's a decimal point. 2s are significant. There's a decimal point. So all of these are called trailing zeros. So they're all significant. So we have 4, which everyone answered correctly. Okay, how about this one? 0.000101. Okay, now we have to remember, everyone who answered got it correct. We have to remember the difference between a leading zero and a captive zero. These ones are definitely significant. This is a captive zero, it's significant. Although there is a decimal point, these are called leading zeros, which don't help with the accuracy, and they're never significant. They're just placeholders. Only if it had zeros at the end would they be significant. So yes, there's only 3 sig figs in this one. Now I think this is our last problem for today, 1.0111. How many sig figs are there? For the most part, everyone got it correct. All non-zero digits are significant. And this 0 is a captive 0, so it's significant. So there's 5 significant figures. So to recap what we learned today, we learned about Dalton's atomic theory. We learned about atoms. We learned about protons, neutrons, electrons. We talked about the atomic number, which is the number of protons, which is Z. Atomic mass, which is A. We talked about the nuclide symbol, which is combining everything. And we talked about the importance of sig figs. So later today, I'll be posting a homework. It's a Google quiz. There's going to be 6 questions. It's going to be pretty short and cover what we have learned in the lecture. So I'd highly suggest you to do it if you have time. I'll post the the lecture slides, and I created lecture notes as well this time, and I'll post them on Google Classroom for you to have. And that's it, guys. Thank you for joining this lecture.